In this class, I am going to explain about band pass filter. So I already told you. So this band pass filter definition. So see, if you take the graph between amplitude of the signal versus the frequency, this is the graph. It is lower cutoff frequency F1, upper cutoff frequency F2. This band pass filter is a filter which will allows this band of frequencies and attenuates the signals below the lower cutoff frequency and above the upper cutoff frequency. So here I can say that this is the pass band. It is a pass band and these are the stop bands. This is also stop band. Okay. So from the definition of this band pass filter, we can define it. It is a filter which will attenuate the signals having the frequencies below the lower cutoff frequency and above the upper cutoff frequency, and allows this band of signals. So that is nothing but it is a pass band and this is stop band. Next, in this construction of this band pass filter, we have the two types of networks, that is T type of network and pi type of network. So in that networks we have the series branches or series arms and shunt branches or shunt arms. So this band pass filter can be represented like this. This is L and this is C. Here this is L, C. L and C. So it is a T type of network in which these are the series branches, this is shunt branch or series arm, shunt arm here. These series arms are constructed with the series resonant circuit having inductance value L, it is inductance and it is a capacitance. It is constructed with, that means the shunt arm is constructed with parallel LC circuit. Here Z1 is equal to this is a series branch, actually it is Z1 by 2, it is Z1 by 2 and this is Z1 by 2. Now it is Z2. In T type of network representation, in the case of filters, we can represent these series branches like this and shunt branches like this. And coming to this pi type of network, here this series branch is represented with a series resonant circuit, series LC resonant circuit, and shunt branches are represented with parallel resonant circuits like this. Now this is a parallel resonant, it is a parallel LC circuit which will have the resonance frequency some omega naught. That means this is resonant, it is Z1, it is 2Z2, this is also 2Z2. We know that Z1 is equal to JXL1 minus JXC1. Here this XL1 is the reactance offered by these inductances and XC1 is the reactance offered by these capacitances. So this series branch can be represented like this: Z1 is equal to JXL1 minus JXC1. Next, Z2 is equal to, this is the parallel LC resonant circuit which can be represented, here it is JXL2 it is jxl2 is in parallel with minus jxc2. Now if I write this j into xl1 is nothing but it is omega l1 minus j into 1 by omega c1 here. Now z1 by 2, if z1 is like this, then z1 by 2 is equal to here 1 by 2 into j omega l1 minus j into 1 by omega c1. So I can rewrite as j omega into l1 by 2 minus j into omega into c1, sorry, it is 2 into c1. So if I multiply this 2 with the c1, it will become 2 into c1. That means this inductance I can write as it is not L1, it is L1 by 2, L1 by 2, and it is not C1, it is 2C1. Okay. If I divide the impedance with 2, this inductance will become half and capacitance will be doubled here. Similarly, here in this case, here also it is L1 by 2, it is 2C1. This Z2, it is XL2 is in parallel with XL2 is in parallel with that means in inductance L2 and it is C2. There is no doubled or there is no half terms here, so that I can write these values as it is L2 and C2. Now if I write this Z2 is equal to j into xl2 is nothing but omega l2 into minus j divided by omega c2. If these two reactances are in parallel, equivalent reactance will be z1 z2 by z1 plus z2, like that. The formula is there, r1 r2 by r1 plus r2. So that is what I am writing here, j omega l2 minus j divided by omega c2. Now I need to find here in case of pi network, we already know that it is L1 and it is C1 because it is Z1. For this Z1 it is L1 and it is C1 here. So 2Z2. So in case of 2Z2, if I multiply with 2, this Z2 is multiplied with 2, I can write as 2 into j omega L2 into minus j by omega C2 divided by omega L2 minus j divided by omega C2. Just I multiplied with 2. Now I can write as j omega into 2L2 into minus j by omega C2 divided by omega L2 minus j divided by omega C2. If I multiply and divide with 2 here, then what happens we'll see here. So this 2 I can write as j omega 2L2 into minus j into 2 divided by omega C2 divided by 2 into omega L2 minus j divided by omega C2, and I can write it as j omega into 2L2 into minus j divided by omega into, if I bring this 2 in the numerator to the denominator, then it will become C2 by 2. And this one also, if I multiply with 2 here, it will become omega into 2L2 minus j into 2. If I bring this 2 from numerator to the denominator, it will become omega into C2 by 2. Finally, what I want to say here is, if I multiply this shunt branch with 2, multiply this shunt branch impedance with 2, this inductance will become 2L2, it is 2L2, and this capacitance will become half, it is C2 by 2. So that is the first point that you need to understand in this band pass filter. That means drawing the T and pi type of networks for band pass filters. That is construction of these band pass filters. Next thing here in this construction itself, we need to understand that this is a series resonant circuit. It is a parallel resonant circuit. This is series resonant circuit. Resonance frequency is equal to the parallel resonance circuit frequency. That means these two resonance frequencies are made equal. That is another point that you need to understand in this construction. For example, this series resonance frequency is omega naught. This parallel resonance frequency is also omega naught. Now, let us consider the frequency of under resonance frequency, under resonance condition, we know that XL1 is equal to XC1. Since this is represented with the subscript of 1 here, it is XL1 is equal to XC1 under resonance condition. XL1 is equal to XC1 means it is omega L1 by 2. Here the inductance value is L1 by 2. It is omega L1 by 2. Sorry, I will write it here. Omega L1 by 2 is equal to XC1 1 by omega. In place of capacitance, it is doubled here, so it is 2C1. This 2 and this 2 will get cancelled, since we are assuming that this is the frequency omega naught is the resonance frequency. So omega naught square L1C1 is equal to 1. Now omega naught square is equal to 1 by L1C1, or omega naught is equal to resonance frequency is equal to 1 by square root of L1C1. Next, if I consider this shunt branch here, then that is XC2 is equal to XL2 is equal to XC2, or XC2 is equal to XL2 under resonance condition. Now XC2 is 1 by omega naught. C2 value is same as that of C2, omega C2, and XL2 omega naught L2. If we rewrite this, omega naught square L2 C2 is equal to 1, omega naught square is equal to 1 by L2 C2, omega naught is equal to square root of L2 C2. So this frequency, we should make the resonance frequency of series branch or series R is equal to the resonance frequency of the shunt R, that is omega naught. So both are same here. So it is, let us consider it is equation number 1, it is equation number 2. From equations 1 and 2, 1 by root L1 C1 is equal to 1 by root L2 C2. From this, 1 by L1 C1 is equal to 1 by L2 C2. So from this, L2 by C1 is equal to L1 by C2, or from here itself it is L1 C1 is equal to L2 C2. From this I can write L2 by C1 is equal to L1 by C2. Why I am taking this expression, you will come to know after some time. So this is L2 by C1 is equal to L1 by C2. So this is about the construction, and from that construction, this is the expression that we got after we make the resonance frequency of the series branch is equal to the resonance frequency of the shunt branch. Now, next thing here is, this is the nominal impedance. This nominal impedance, how to calculate the nominal impedance? So nominal impedance, it is normally represented with K. We know that Z1 Z2 is equal to K square for a constant K. filters. So now what is Z1 here? We calculated this Z1 is equal to here Z1 is equal to J into omega L1 minus J divided by omega C1 for a series branch, and if I take the J here, J as a common, omega L1 by omega C1, and that is equal to J into omega square L1 C1 minus 1 divided by omega C1. So this is the value of Z1. Now what is Z2 here? Z2 is equal to this shunt branch impedance. So that is XL2, JXL2 is in parallel with minus JXC2. So here JXL2 is in parallel with minus JXC2. So here JXL2 into minus JXC2 divided by JXL2 minus JXC2. So if I replace this L2 XL2 with omega L2 and XC2 with 1 by omega C2, J into J here is minus 1 and minus will cancel to each other and will get a positive sign here. So it is omega L2 into 1 by omega C2. Now it is omega L2 minus 1 by omega C2. It is equal to omega L2 divided by omega C2. It is omega square L2 C2 minus 1 divided by, I need to take the J as a common here. J should be taken out from these two terms here. So it should be J omega square L2 C2 minus 1 divided by omega C2. So that is equal to, if I bring this J term from the denominator to the numerator, it is minus J. This omega C2 will get cancelled. Minus J into omega L2 divided by omega square L2 C2 minus 1, or it is J into omega L2 divided by 1 minus omega square L2 C2. Okay, it is Z2. So this is the value of Z1 and it is the value of Z2. Now we will multiply these two things here to find out this K. So Z1 Z2 is equal to, Z1 value is J into omega square L1 C1 minus 1 divided by omega C1 into Z2 here is J into omega L2 divided by 1 minus omega square L2 C2. This J, if I multiply with this J, it will get minus 1. J square is equal to minus 1. Then I can rewrite this expression as, instead of writing omega square L1 C1 minus 1, I will write it as 1 minus omega square L1 C1, because J into J is minus 1. So it is 1 minus omega square L1 C1 divided by omega C1 into omega L2 by, it is 1 minus omega square L2 C2. And we already calculated that this L1 C1 is equal to L2 C2. If I substitute this L1 C1 with L2 C2, then I will get it as 1 minus omega square L2 C2 divided by omega C1 into omega L2 to 1 minus omega square L2 C2, because here since L1 C1 is equal to L2 C2, I just replaced this L1 C1 with L2 C2, and this term and this term both are same here, will get cancelled. So here this omega will get cancelled, so it is L2 by C1, that is equal to Z1 Z2. L2 by C1, or we can also write it as L2 by C1 is equal to L1 by C2. So it is L1 by C2. So Z1 Z2 is nothing but K square. So K square is equal to L2 by C1 or L1 by C2. So from this we can get the value of k. K is equal to square root of L2 by C1 or square root of L1 by C2, or k square is equal to L2 by C1, that is equal to L1 by C2. Next thing here is cutoff frequencies. We need to find out cutoff frequency, but in case of this band pass filters and band stop filters, we will get the relation between the lower and upper cutoff frequencies with the resonance frequency. In case of band stop filter and band pass filter, we need to derive this one, that is omega naught resonance frequency, the relation between this resonance frequency and this lower and upper cutoff frequencies. This is the condition that I am going to prove here. That is, this resonance frequency is the geometrical mean of lower and upper cutoff frequencies. Or if I replace this omega with 2 pi f, f naught is equal to square root of 2 pi f1 into 2 pi f2. That is equal to f naught is equal to, so 2 pi f naught is equal to 2 pi 2 pi. If I take these 2 pi term from this square, it is 2 pi square, that is 2 pi, and square root of f1 into f2. This 2 pi, this 2 pi. So f naught is equal to square root of f1 into f2. So this is what I need to prove in case of this band pass filter and band stop filters. This is the condition. So to prove this relation between this one, I am taking this Z1 by 4 Z2. We know that Z1 by 4 Z2 is equal to minus 1. This is one condition. To get the relation between this, to get the expressions for cutoff frequencies, it is one of the expression. Now from this it is cutoff frequency. You can write it as cutoff frequencies. Okay. So Z1 by 4 Z2 is equal to minus 1. If I write Z1 is equal to minus 4 into Z2 here, and I will multiply this this expression with Z1. That means both sides I will multiply with Z1 for this one. Z1 is equal to Z1 into Z1 is equal to minus 4 Z1 Z2. We know that it is Z1 square. Z1 square is equal to minus 4 into Z1 Z2 is nothing but k square, that is 4 into k square. So if I take a square root on both sides of this equation, it is Z1 is equal to plus or minus square root of minus 4k square. So it is plus or minus, if I take 4 out of this square root, I will get 2 here. If I take this minus sign out of this square root, I will get the complex imaginary quantity, that is 2jk. So this is the relation important for getting the relation between this resonance frequency and cutoff frequencies, and also this expression is used to get the values of these L1, C1, L2, C2s to construct the filters. So finally we need to design a filter using the values L1, C1 and L2, C2, and he will give the values of these cutoff frequencies F1 and F2 value. He will give F1 and F2 value along with this nominal impedance K. He will give these values, K value and F1, F2 values, and we need to design the circuit for band pass filter or band stop filter or low pass filter or high pass filter. So for that we should have the expressions of this L1, C1, L2, C2s in terms of K and these frequencies F1 and F2. So to get this relation, we should use this expression, that is Z1 is equal to plus or minus 2jk. Or to get this relation also, we will use this relation here. Z1 is equal to plus or minus 2jk. Next thing here, what is Z1 here? Z1 is nothing but it is an impedance of a series arm. impedance of a series R. Actually Z1 is equal to j omega L1 minus j divided by omega C1. So series R impedance, this one, jXL1 minus jXC1. Here at lower cutoff frequencies means this omega value is lesser value. In upper cutoff frequencies, omega value is higher value. So if the omega value is less at lower cutoff frequency, 1 by omega value will be high. 1 by omega value will be high. Means at lower cutoff frequencies, at lower cutoff frequencies, this XL1 or XL1 is less than XC1 because this omega value is less. So this omega L is nothing but XL. So this value will be lesser than XC1. So that this impedance will be negative. So Z1 is negative at lower cutoff frequency. Okay. That means what I want to say here is second thing, Z1 is positive at higher cutoff frequency. Finally, the negative value of Z1 at lower cutoff frequency is equal to positive value of Z1 at higher cutoff frequency. So this condition I am going to use here, that is minus Z1 at lower cutoff frequency is equal to, so it is minus Z1 at omega is equal to omega 1, omega is equal to omega 2. This is what I am going to write here. So what is this Z1 here? This is the Z1. So I will write it as minus Z1 value is j omega 1 L1, where omega 1 is the lower cutoff frequency, minus j divided by omega 1 C1 is equal to, it is at higher cutoff frequency, omega value, positive value, j into omega 2 L1 minus j divided by omega 2 C1. From this condition, we will get this relation, omega naught is equal to square root of omega 1, omega 2. So let me derive that. If I take this j from these two terms, then it will be minus j into omega 1 L1 minus 1 by omega 1 C1. It is equal to j into omega 2 L1 minus 1 by omega 2 C1. It is equal to this j will get cancelled here. Now I can write it as 1 by omega 1 C1, because if I multiply with minus 1, this will become like this, omega 2 L1 minus 1 by omega 2 C1. Now if I bring these two terms to this left side, it is 1 by omega 1 C1 plus 1 by omega 2 C1 is equal to omega 1 L1 plus omega 2 L1. So this can be written as, if I take C1 as a 1 by C1 as a common, it is 1 by omega 1 plus 1 by omega 2. That is equal to same thing, omega 1 L1 plus omega 2 L1. Now 1 by C1, if I take LCM as omega 1 omega 2, it will become omega 2 plus omega 1, that is equal to, if I take L1 as a common here, it is omega 1 plus omega 2 into L1. Now this omega 1 plus omega 2, this omega 1 plus omega 2 will get cancelled here. Finally 1 by omega 1 omega 2 into this C1 is equal to L1. So from this 1 by omega 1 omega 2 is equal to L1 C1, omega 1 omega 2 is equal to 1 by L1 C1. And we know that from the concept of this resonance frequency, omega naught square is equal to 1 by L1 C1. So I can replace this 1 by L1 C1 with omega naught square, the omega naught square. So this is omega 1 omega 2 is equal to omega naught square. So from this omega naught square is equal to omega naught square is equal to omega 1 omega 2, omega naught is equal to square root of omega 1 omega 2, or f naught using this one. Same expression, this like this, f naught is equal to square root of f1 f2. So this is the relation. This is the relation that we need to understand in this cutoff frequencies concept. Next thing, after deriving this one, next concept here is how will be the variation of the alpha. Okay, let me first number it. It is 13, 14, is 15. So the variation of attenuation constant alpha, and beta is nothing but phase constant beta, characteristic impedance Z0 with respect to frequency. I am going to draw that. So here variation of alpha comma beta comma Z0 with respect to frequency f. So to understand this variation of alpha beta Z0, characteristic impedance Z0 with respect to frequency, we should understand the variation of all these three parameters with respect to frequency in case of low pass filter and high pass filter. If you understand that variation in low pass and high pass filters, then it is easy to understand this band pass filter variation. So this band pass filter is constructed with a high pass filter followed by the low pass filter. What that is, I will explain. See, it is band pass filter. In this band pass filter, it will allows this band only. It is pass band, we know that. It is one frequency FC1, it is another frequency FC2. Okay, it is amplitude of the signal. Here in low pass filter, in high pass filter, it allows high frequency signals only. High frequency signals means it is, suppose it is for high pass filter, it is an amplitude for high pass filter, it is band pass filter. So this is one cutoff frequency for a FCH high pass filter. So this is a pass band, we know that it is a frequency. And for low pass filter, for a low pass filter, it will let us take this one as FCL, cutoff frequency for low pass filter. It allows the low frequency signals only. So it is pass band. Now if you combine this high pass filter followed by the low pass filter, then I will get these two. You can see this one. Okay, that means this pass band, this is the pass band, this is the pass band. This high pass filter will not allow below this cutoff frequency. This low pass filter will not allow above this cutoff frequency. Similarly here also, this band pass filter will not allow this cutoff frequency and will not allow these signals above this cutoff frequency. Finally, what I want to say here is this band pass filter will be constructed with the help of the high pass filter followed by low pass filter. Means, let me take the variation of alpha. It is a frequency f and it is alpha. Next variation of beta also I will write here. Okay, it is beta. So to understand this, we should have the idea of variation of this alpha, beta in case of this low pass filter and high pass filters. I am searching for it. Yeah. This is a low pass filter, the alpha and high pass filter. Yeah. This is a high pass filter variation of the alpha and beta. So it is for high pass filter and it is for low pass filter. It is having this band pass filter will having the two cutoff frequencies FC1 and FC2. Here we will represent them as F1 and F2. It is F1 and this is F2. Between this F1 and F2 there is a resonance frequency will also be present, that is represented as F0. Same thing, you extend this F1 here, F0 here, and this F2 is also here. Okay. So in case of low pass filter, the attenuation constant variation, it is followed by high pass filter. It is constructed with high pass filter followed by the low pass filter. So I need to take this one as a higher cutoff frequency. So this one has a higher cutoff frequency in case of high pass filter. So if I draw this one, if I draw these lines here, F0, F1, it is also F0, it is F0, F2. Okay. So first high pass filter cutoff frequency is this one. So it will be like this. Means the graph, if I draw the graph for it, this will be like this. Variation of alpha. Next thing, it is followed by low pass filter. It is low pass filter. So for low pass filter, this is another cutoff frequency. It will be, this alpha variation will be like this. This is the alpha variation. So finally, the variation of alpha first follows the high pass filter, then after low pass filter. Okay. Similarly, this beta also, the variation of beta with respect to frequency, this band pass filter, since it is constructed with the help of this high pass filter followed by low pass filter. So this is the high pass filter beta variation. So for that, it is a first cutoff frequency. So it is F1 is the first cutoff frequency is F1. It is F0 and it is F2. Now this beta variation, here, variation of beta. First, high pass filter, below the cutoff frequency it is pi. So cutoff frequency of the high pass filter. First, high pass filter, the variation, while we are drawing the variation of this beta, we should consider the high pass filter variation of the beta followed by the low pass filter. So here below the cutoff frequency, the value of this beta is minus pi. So it will start from minus pi. So this is minus pi. Okay, this value is minus pi. Next, so it will it goes like this. So it goes like this. It will go like this up to resonance frequency f0. Now coming to this low pass filter variation of beta. So this low pass filter variation of beta, this is the low pass filter variation of beta. So it is a lower cutoff frequency, it is the cutoff frequency of the low pass filter. So this one is same as that of that one. So this one, so this will be like this. This curve will follows like this, and after this cutoff frequency, anyway, it is equal to pi. This value will be equal to pi. So this is the value of this one is pi. So this is the variation of this alpha and beta with respect to frequency, and we know that this is the pass band. It is the pass band. Here also it is the pass band. These are the stop bands. It is stop band. This is stop band. Same thing here also. It is stop band. This is stop band. Okay. Next, the variation of characteristic impedance with respect to frequency. Characteristic impedance. So this is the frequency f. It is Z0. Okay. So for a high pass filter, it is a high pass filter frequency, cutoff frequency. It is the low pass filter cutoff frequency. So f1 and it is f2. It is the resonance frequency f0. Okay. So high pass filter Z0. So this Z0 will have the Z0t and Z0 pi. Z0t and Z0 pi. So this is, I think it is high pass filters. It is high pass filter variation of this Z0 means characteristic impedance with respect to frequency. It is the cutoff frequency. Here it is the cutoff frequency f1. So this is Z0t. This will follows like this. So it is Z0t will be like this. So this the value of k, and Z0 pi, it will starts from infinity. And it is Z0 pi. Okay, so it is Z0t, it is Z0 pi. Okay, and this is the value of k. This is the value of k. Okay, so this is Z0t and it is Z0 pi. It is high pass filter. This one, it is Anyway, it is a stop band. Here it is a stop band. So it is a stop band. It is pass band. Pass band. Okay. This one is stop band. Okay. So next thing, it is high pass filter variation of the Z0. Now it is low pass filter. So it is this one. This Z0 T will falls from K to 0. It is the cutoff frequency for low pass filter. It is the upper cutoff frequency of band pass filter. So these will follow this. It will follow like this, and it is Z0 T, and this Z0 pi will follows this curve. So this curve is Z0 pi, and this curve is Z0 T, and this band is pass band, this band is pass band, and this band is stop band. So this is how we need to draw this variation of alpha, beta, Z0 with respect to frequency. This is 16. Next thing here, design of a filter. This is an important thing. So for doing the problems, this concept is very important. Next 17th page. So design of a filter. Design of a band pass filter. Okay. So to design this band pass filter, design means we need to construct. So I need to construct this filter. Means I need to find the values of L1, C1, L2, C2. If I know these values, I can construct this network using these inductors and capacitors by placing the proper values of this L1, C1 along with L2, C2. So to design this filter, we need to know the values of L1, C1, L2, C2. To find these values of L1, C1, L2, C2, what I am doing here is I am using the expression. What that is here is Z1 is equal to, where is that expression? Plus or minus J2K. We already found that expression. The 7th. Z1 is equal to plus or minus J2K, is 2JK. So I am using this one here. Z1 is equal to, we know that it is plus or minus 2JK at lower cutoff frequency, the value of Z1 is negative. So Z1 is equal to, at omega is equal to omega 1, that is equal to minus 2jk. I am using this expression to find the values of L1, C1, L2 and C2. So Z1, what is Z1? J omega L1 minus J divided by omega C1, that is equal to minus 2jk. Just I am taking this J as a common here. If I take J as a common, omega L1 minus 1 by omega C1 is equal to minus 2j into k. So from this j and this j will get cancelled here. So omega square, sorry, it is omega 1. At omega is equal to omega 1. So it is omega 1. It is omega 1 square L1 C1 minus 1 divided by omega 1 C1 is equal to minus 2k. And I can rewrite it as omega 1 square L1 C1 minus 1 is equal to minus 2k omega 1 C1, and it is 1 minus omega 1 square L1 C1 is equal to 2k omega 1 C1. Now this one, we know that omega naught square is equal to 1 by L1 C1. We already find that derivation, that is omega naught square is equal to, where is that omega naught square is equal to 1 by L1 C1. So I am using that thing here. So L1 C1 is equal to, from this L1 C1 is equal to 1 by omega naught square. So I am substituting this omega naught square in place of L1 C1, 1 by omega naught square. So 1 minus omega 1 square divided by omega naught square is equal to 2k omega 1 C1. 2k omega 1 C1. Now I can write it as 1 minus omega 1 by omega naught whole square is equal to 2k omega 1 C1. This is equal to 1 minus f1 by f naught, f1 square by f naught square is equal to 2k into 2 pi f1 C1. Now it is 4 pi k f1 C1 is equal to, if I take LCM of f naught square here, f naught square minus f1 square divided by f naught square. Now it is 4 pi k f1 C1 is equal to f naught square. You know that it is I think it is what it is, f1, sorry, here itself I can, sorry, writing as it is here, that is 1 minus f1 square divided by f naught square. So 1 minus f1 divided by f1 square divided by f naught square is f1 f2. Using that that relation, f naught is equal to square root of f1 and f2. F naught square is equal to f1 f2. So this f1 will get cancelled here. It is 1 minus f1 by f2. So it is f2 minus f1 divided by f2. So what it is, 4 pi k f1 C1. My intention is to find the value of C1, that is equal to f2 minus f1 divided by 4 pi k f1 f2. This is the formula that we need to remember for solving the problems. So the examiner will ask the questions like this: design a filter, design a band pass filter, like that. He will give the question and he will give the values of these cutoff frequencies, f1 value, f2 value, along with this k value also, design impedance or nominal impedance. So from this, if you know this formula, directly we can find the C1. So if you find the C1 value, now we can find the value of L1 using this relation. Here we know that L1 C1 is equal to 1 by omega naught square. Now L1 is equal to 1 by C1 into 4 pi square f naught square. Instead of omega naught, I rewrote that omega naught as 2 pi f naught. So it is like this. So C1 value just now we calculated as, it is f2 minus f1 divided by 4 pi k f1 into f2 into what is 4 pi square into, in place of f naught square it is f1 and f2. This f1 f2, this f1 f2, 4 pi 4 1 pi here. So this value of L1 here is what it is, if I bring this term to the numerator, this k divided by this 1 pi into f2 minus f1. So this is this is the value of L1 which is required to design a filter. So C1 value we got and L1 value also we got just now. And also I need to find the values of L2, C2. For that I will use this expression. What that expression here is, k square is equal to L2 by C1. So that is we know that so k square is equal to, we know that k square is equal to L2 by C1. So L2 is equal to C1 into k square. So L2 is equal to, C1 value is f2 minus f1 divided by 4 pi k into f1 f2 into k square. So this k and this k will get cancelled. So finally what we got here is L2 is equal to f2 minus f1 into k divided by 4 pi f1 f2. So this is the value of L2 that we need to place while we are designing the band pass filter having the cutoff frequencies f1 f2 and design impedance k. Next, the value of C2, L1 value obtained, C1 and L2 values also we derived here. Next thing here is the value of C2. Same thing, I will use this expression, L1 C1 is equal to L2 C2, or k square is equal to L1 by C2. From this, C2 is equal to L1 by k square. So C2 is equal to, L1 value is k divided by pi into f2 minus f1 into k square here. This k will get cancelled. So C2 is equal to 1 by pi k into f2 minus f1. So this is the value of C2 we should place in designing of band pass filter. So for solving the problems, it is enough to remember these formulas. If you know these formulas along with the circuit, that circuit here is this circuit, then here it is L1 by 2 2C1, L2 C2, L1 by 2 2C1. It is a T type of network and pi type of network. Here forgot to write, here it is T type band pass filter. It is pi type band pass filter. So after finding these values of L1 C1 L2 C2, just if you substitute here in this T network and pi network, then that is the answer for that question. Alright, so this is about the complete information of this band pass filter. Next class I will explain band stop filter.